can turn off this fan, the second switch. Yeah. Okay. Today's class will mostly be looking at the typical kinds of structural components that we will be considering throughout this course, but more from the point of view of motivation as to why those kinds of shapes and sizes are so common in aerospace engineering. In fact, they are common in a lot of other transportation engineering sectors as well, be it ships or automobiles, etc., but more so in the case of aerospace. But before we head to that, we need to understand a little more in terms of one of the bases of classification we did last time. So we will elaborate a little more on that, because that is what will set the background for the kind of geometries that we would be interested in pursuing for structural analysis. So let's look at these loads. First of all, from the point of view of the sources, and we know that flight vehicles are flying in the air mostly, though there are of course those which fly in space, but those which fly in air predominant, many more that we typically deal with, and there one of the dominant loads is the air load. So the air load is essentially coming as a pressure distribution around the surface of the aircraft or whichever flight vehicle we are looking at, but also in terms of the shearing forces. And the shearing forces become much more important when you are dealing with lower Reynolds numbers, and especially for the kind of interest that has been cultivated in aerospace for almost last 2-3 decades in terms of drones, micro aerial vehicles and nano aerial vehicles, where MAVs or micro aerial vehicles typically simulate bird-like flight, and the nano aerial vehicles simulate insect-like flight, though there are not just flapping wing versions but also fixed wing and rotary wing versions of these typical smaller drones. There the Reynolds numbers are very low, which means the frictional forces are large and the viscosity has to be considered. So typically the pressure distribution you integrate in such a way that you end up in terms of resultant forces, the lift and the drag that you are all very familiar with. In addition, there is a pitching moment, and depending upon the kind of flight, sometimes there could be rolling moments, yawing moments and side drift forces as well. Then we come to other than the airflow loads, the loads which are coming due to the landing gear, due to an impact of a bird, the impact of a tool drop, even during maintenance on the ground, etc. Essentially concentrated loads that we are talking about. Then the concentrated loads could also include the attachment of certain structures, like let's say the engine pylon to the wing or to the fuselage. At that location there is a concentrated load. But truly speaking, concentrated load is an idealization we structural engineers make for a first cut analysis. There is no such thing as a concentrated load, because a load can in reality rarely act at a particular point or even a line. It is usually over a surface area, and sometimes the surface area is very small. Then we idealize that location of the load to a point, which we call as a concentrated force. Or it could be a line when we call it a distributed force along the line, typically give it in the form of a force per unit length, a Newton per meter kind of an SI unit. So that is as far as concentrated loads are concerned. So remember that it's purely something kind of an approximation that we are making for simplicity. In reality, all of them are distributed loads, just that how large a load is being distributed in how small an area, then sometimes we tend to deal with it as concentrated loads. Much simpler to do the mathematics over there. Then of course the self weight of the aircraft, though for typically rigid body dynamics we would assume all of the weight to be acting at the center of mass or the center of gravity, we would in the more realistic case of understanding the load distribution look at the actual weight of each of the structural components, and because of the various materials used, various geometries used, so it's kind of a distributed load and that has to be the weight distribution not just within the aircraft but also that of the empty aircraft itself. Then there are also loads which come because of environmental changes like humidity and temperature. Together they are known as the hygrothermal stresses, which are caused by the aircraft flying, let's say, in extreme temperature conditions or conditions where the temperature changes quite a bit or the humidity changes quite a bit, especially when you are flying between dry areas and or fairly wet areas like over the ocean. Some amphibious aircraft are much more susceptible to this, and again there are specific materials which are much more prone to these kinds of issues. In particular, composites that are mostly used in the aerospace industry, especially polymer matrix composites, can absorb the water and therefore can either swell and or change its properties, typically to inferior properties, and therefore there is an issue with them. So that is another source of the loading. The next is of course the thrust coming from the engine. So except for a few fighter aircraft, you would have mostly multiple engines, and each of these engines are going to offer a thrust, and that thrust line is going to be away from the CG, and therefore there is not only going to be a force but also a moment coming where these are attached. Once again, the attachment are not points or lines actually, but actually areas like what we talked about when we said that these are not concentrated loads. So there we were talking about the engine weight, here we are talking about the thrust coming from the engines. Then the next thing is what in dynamics you might have studied as the D'Alembert's force. So essentially the Newton's law, which is F is equal to ma, can be written as F minus ma equal to 0. You treat it as a quasi-static problem where the ma becomes another additional force that you are equilibrating the rest of the forces acting on the system with. So then you talk of the inertial forces, and we drew the flight envelope in the previous class where we talked about V versus N, or rather N versus V, and there the number of G's loads that are coming at any given velocity, there is a limit to them, and as long as you're operating within that, it's safe. But then there are also gusts which happen every now and then because of turbulence in the air, and that can raise or lower these G values quite substantially at times, and therefore the flight envelope is typically first drawn without the presence of gust, and then corrections are made to typical range of gusts, giving extra order of extra factors so that we can account for gusts which are more than what is typically observed in the flight regimes. Then the other aspect, especially when you're dealing with high altitude aircraft, even the kind of aircraft that you flew from the US to here, typically flying at an altitude where the typical atmospheric pressures are so low that the body is not very capable of handling, the human body is not very capable of handling that. So typically passenger aircrafts are internally pressurized. They are not pressurized to as high a pressure as we have at the sea level or the ground level of most locations, but a slightly lower pressure, and that's what sometimes can cause ear issues and a lot of different issues for different people. But typically those who are not used to very long haul flights and things like that. But from a structural point of view, that internal pressurization makes it almost like a pressure vessel, though typical pressure vessels that are dealt with in mechanical engineering, etc., the pressures are very, very large. So in other words, there is a differential pressure that is important between the internal pressure and the external pressure. The aircraft is flying at a certain altitude, so you know the atmospheric conditions over there of the standard atmosphere and make corrections for specific locations and other things that you're, or seasons that you're aware of, but otherwise you know the outside pressure, you know what pressure you're putting the cabin into, and therefore the difference is what we are talking about over there. So these are the many sources of loads that can come on the flight vehicle, and based on which we need to make decisions in terms of how we are going to shape and size the structural components which are going to be handling that. Now purely in terms of the resultant forces, because that's how we as analysts, rather than an experimental sensor determination, it's more from an analyst's point of view. We always deal with resultant forces and resultant moments, and in fact we would call forces and moments together as a single entity called generalized force, just like we would call rotations as part of displacements and call them generalized displacement. So instead of relating force and moment by a separate force and displacement by a separate equation, and a moment and rotation by a separate equation, we'll combine all of these into matrix equations where we call all of the forces and moments together as a generalized force, and all of the displacements and rotations together as a generalized displacement. So then but nonetheless, in terms of the actual differences of these concentrated forces that can occur, or distributed forces, are essentially of two types, as you know: those which are normal to the surface on which they are acting, resulting in normal stresses of course, and those which are shearing in nature. In other words, they are tangential to the surface on which they act, and therefore they are called as shear forces. Now normal forces in turn are divided into two depending upon the sign or direction in which those normal forces act. Those which are pushing into the structural material of the component that we are interested in are essentially causing compression. Those which are pulling out the material are essentially causing extension or change in length, which is positive. So we have two types of forces which are normal, and correspondingly we will have two types of normal stresses as well: compressive and extension, or tensile stresses as we call it. And as we increase those stresses to a certain limit, each of them will fail in a certain level depending upon the material properties, and those will be the ultimate tensile strength or yield strength depending upon the specific material, and the ultimate compressive strength on the other direction. As far as the shear is concerned, again it can be divided into two parts. This is something that most students are not very familiar with, or get confused about. So it's very important to understand this distinction. Just like in the case of normal stresses, we had a distinction based on the sign, whether it is a push or a pull. Here it's based on which surface it is acting. So typically, as you know, most of these flight vehicle structural components are thin walled structures, typically like this tabletop that you see over here. So we can think of modeling this entire table as just its reference surface, which is typically the mid surface of this. Instead of modeling the entire finite thickness that is there, we lump all the properties to a point which is in between. May or may not be the same, the mid plane or a mid surface. It could be anywhere in between. We call it a mid plane when this is a plate, and we call it a mid surface when it is a shell-like structure which is having already some initial curvature even before you apply any load to the particular structure, right? So when you have something like that, we talk of shear, we know that already we have talked about it as something which is tangential to the surface on which it is acting, as opposed to a normal which is perpendicular or orthogonal to the surface on which it is acting. So if this is a surface and I push this with a certain force or a pressure, then essentially it's a normal. Whereas if I'm trying to rub into it, it's essentially a shear. So from the air loads itself, we saw the pressure loads coming from the air are essentially normal, whereas the in the boundary layers that are there, especially for low Reynolds number aircraft, you typically have these shearing forces coming from the viscosity of the fluid which is flowing, which is air typically. So now, though all of them are shear, there are certain things which are called in-plane shear and certain things which are called out of plane or transverse. So this is what needs to be remembered. So as I said, because of the fact that we are modeling this actual 3D body as a plane or a surface, what happens is that which is tangential to the plane. So in other words, for example, if I am applying a shear in this particular direction or I am applying a shear in this particular direction, then essentially it is this shearing stress is in the plane of the structure, and that's what is called as the in-plane shear that you have over here. On the other hand, you know that though you are modeling this as a zero thickness, in reality it is a finite thickness, and therefore there can be stresses which are acting in this direction or this direction as well. So which is essentially in the smaller thickness direction as opposed to the width and the length, which are fairly large. So those stresses are typically what you are calling as the transverse stresses. And these transverse stresses along with transverse normal stresses typically play a huge role in composites, because one of the main ways in which composites fail is through delamination, because you're going to have a laminated structure. In other words, many layers of different angles of the plies one over the other, and there can be a shear stress which occurs in between and or a normal stress which occurs between any two adjacent layers, and these can cause these two layers to debond or separate out, and that is what we call as the delamination, right? So that delamination, if you need to understand properly, you do need to get these transverse stresses, especially if you're doing a plate analysis the way I described it. If you're doing a beam analysis, let's say this is a beam, you're reducing the cross-sectional area, which is having smaller dimensions compared to the length, into a point, and therefore a line if it's a straight beam, or a curve if it is a initially curved or twisted beam. So when you have something like that, you are typically going to have, like, once again, in plane and transverse stresses. These transverse stresses are those which are on this particular cross section, whereas the in plane are on any of these edges, whereas whatever shear stresses are acting on the cross section are essentially your transverse stresses. And especially when you have a thin walled cross section like this, it's essentially along the thickness that is the dominant transverse shear stress, which can cause these layers to peel off either at the edge or somewhere in between. At the edge, sometimes it's easier to detect even through visual inspections, but if it's interior, not even, it becomes dangerously large. So it's very important to understand that, but you would see that many of the simpler theories that we will start with will actually ignore these transverse stresses because of the fact that these are so dominant. In other words, the stresses, we are talking here of course only about forces, but forces are going to result in stresses, and those stresses which come out of these typically in most structures will be much larger in magnitude compared to these. But so what tendency in simpler models is to just ignore this, say it is zero, and deal only with this. Even the transverse normal stress will be left out, and only the those which are associated with the in-plane direction, in-plane normal stresses, both extension and compression, will be taken into account. So, but that's a first cut analysis. But if you're doing only that, then there is a danger that contaminations can occur, and you will not even know about it even in the analysis, leave alone in the inspections, experimental inspections. So the next thing that we need to be familiar with in moments or couples is essentially two types, especially when you're dealing with the kind of structures that we have, plates as well as beams. So we would have one which is a torsional moment or a torque, as we call it, so which is essentially twisting this beam. I would also be twisting this, so I would be pushing this end and pulling this end up, or in other words, I would be having a distributed force which does that. So essentially what is happening is that we are trying to twist it so that the angle between that cross section and this cross section is no longer zero, it is having a change. But it's also possible that even without the application of load, there can be a pre-twist, which is very useful in a lot of different applications. I have touched upon this in a previous class as well. But now we are looking at an actual application of a load torque which is causing that. How can that be in a typical actual flying case? In the case of the aircraft, you have the pressure distribution, which is having a resultant of a lift and a drag and a pitching moment. That pitching moment is essentially acting about the aerodynamic center of the each cross section, which is a airfoil cross section, and that pitching moment about the CG is what is going to cause a certain twist in the whole structure, and that twist is what we are talking about over here. So one source of that is the aerodynamics. The other is also, of course, the things that are attached to the wing, let's say an engine, so that the engine CG, for example, if it is away from the CG of that cross section, you know that there is a moment arm and non-zero moment arm, and therefore there is a torque which is arising out of that. So all those are examples. We're not being comprehensive in including all of them, but just giving sample examples of what can be causing that. The other, of course, is bending. Very obvious, that is one of the dominant loads because of the lift distribution, which is typically elliptic kind of a distribution to start with as a good assumption, but then there are many other better aerodynamic estimates of how the lift is distributed along the wing span, starting with 0 at the tip of the wing and reaching a maximum value at the root of the wing, where the wing is attached to the fuselage. Now, that is a distributed load, and which is acting perpendicular to the velocity direction. So when that is happening, the wing tends to bend upwards. So that is essentially a bending moment that is being caused. So that is the example that we are talking about. So we are talking about the forces and the moments and the different classification of the forces and moments coming from the loads. Are there any doubts about this? Okay. It's gone. So now this is the most important takeaway from today's class, which is in terms of we've always been saying that there are shells or zero curvature shells being plates or beams with both initially curved beams as well as straight beams. So first of all, why do you need to have shells and beams in the case of a flying vehicle structure? Any idea you have in terms of why we use shells and beams? Why not other kinds of structures? Why are these the dominant structural components? Yeah.
Because they can support pressure and distribute it across the surface.
Good. Yeah. So they are capable of doing the function that is required of them, which is essentially the distributed loads and concentrated loads that we saw in the previous slide that can be taken, is what Alexandra is saying. Anybody else? Come again?
The computational time be reduced.
True, the computational time will be reduced, but the computation is only fallout of having such a structure. You have a particular structure because it is good or appropriate for that application. Then whatever is the optimum, we as analysts will have to analyze it. It so happens that what you're saying absolutely right, that it's much more efficient to analyze these compared to 3D structures, because these are going to be much more computationally less intensive in terms of the modeling. Number of degrees of freedom are going to be lesser, etc. But why do the flying vehicles need these shells and beams is what I'm asking right now. Yeah.
Having a thin shell would like reduce the weight, and then having beams to support it makes it less structurally sound.
Yeah, good point. Because weight is the most critical thing determining the performance of an aircraft. For all other things kept the same, if you're trying to reduce the weight, you're going to have either a faster aircraft or an aircraft which has a larger range or which can take more payload, or combinations of all of these. So in many different senses, or let's say if it's a fighter aircraft, many more maneuvers it can possibly do and things like that. So the less the weight, the better, and these kinds of geometries typically lead to better kind of utilization of the material. In other words, anyway you are going to take a certain amount of material to handle these stresses and strains. Put these materials in those locations where the stresses and strains are much more. So when you are trying to do that, you end up with these kinds of shapes. So we'll try to look at it in a more logical step-by-step fashion. So typically when you are looking at any structural part of vehicle, need not necessarily be an aircraft, helicopter or launch vehicle or a missile, or even a satellite, but even those on the ground, be it trains on the tracks or those on the roads, the automobiles, small and large, or even those on the waters, the naval ships, the aircraft carriers and much smaller boats and yachts and things like that. All of them, typically when you're talking about the structural components of that, they have three major functions and triple functions of any vehicular structure. The first thing is that usually you don't have a single structure, you have multiple structures and they are attached to each other, and at the points of attachment they are required to transfer load from one to the other. Let's take the simple example of an aircraft skin. The skin is what is exposed to the airflow. None of the other structural components which are within the skin are directly exposed to the airflow, but most of the air loads are actually taken by those which are inside. How does this happen? The skin takes the pressure, takes the shear and immediately transfers it to whatever it is connected to. For example, it could be connected to a spar, it could be connected to transverse ribs, it will be connected to stringers. We will see examples of all of those and the specific functions of each one of those components whom I named and shamed right now. We will look at the very purposes of that. But essentially the first function that we are talking about is the ability to transmit and also resist. There are certain things which will be resisted at that location and certain things which will be transmitted. So these whatever loads are acting on the vehicle, which we saw in the previous slide coming from various sources, they are all either transmitted and or resisted in a particular way by each structural component. The second thing that you are talking about is that these structures are going to provide a certain shape, overall shape to the entire vehicle. So in particular for aerospace vehicles, this is very important because the shape is what is going to determine your L by D ratios, that is the lift to drag ratios or maximum values of those, and various other aerodynamic parameters which are going to directly have an implication on the performance of the aircraft. So now if that is the case, then the overall shape in the case of aerospace, aerodynamic shape, in the case of naval structures like boats and ships, the hydrodynamic shape, and even in the case of buildings for that matter, the aesthetic shape, essentially it provides the outer look or the outer functionality of containing things like that. So that is the third function that we are talking about. Not only it provides a certain shape so that it maximizes the effect that we desire of the air flowing around this particular structure or water flowing around this particular structure, but we also have, because of the fact that it is the outer structure, everything else that we want to take from point A to point B in a transport, be it cargo, be it human payload or whatever it is, essentially what we are trying to do is to have some kind of a covering for that. Like just like shelter, a static shelter is a home, you typically have a flying shelter which is essentially your aircraft within which you can be, rather than having to hold on to the aircraft and fly on top of it. You will not only affect its aerodynamics, but also it will be very inconvenient for long flights, especially at higher altitudes, if at all possible. So this is the third thing that we have to act as a cover, which is protecting the contents of the vehicle from the environment, which means that the pressures, the temperatures, the humidity and all kinds of other things which come, very similar to the function that this building's walls and ceiling and floor are giving us, and in a static sense the same thing is given by the aircraft's structure. So these are the three functions of what we call as the triple functions of the vehicular structures, which we should be aware of, because this is what will lead us to an understanding that indeed those two on the top of the slide, the shells and the beams, are the most optimal way of handling this kind of a structure. Why? Because if you look at what a beam is, typically you are looking at a very long slender structure. Now if you are having a moment and it is to be distributed or taken to a certain other location where it can be resisted by some other structure, which is essentially transmission, you would see that the beam is the most efficient. And within the beam, if you are looking at the cross section, you are seeing that, for example, if for this to resist a large bending moment, we will very soon see that the moment of inertia about the so-called neutral axis over here has to be very large. In other words, you want to distribute the material farther away from the neutral axis so that it is capable of handling more loads. The closer it is to the center, so-called center of this, which is more layman's way of talking about it, but we will talk about it in a more specific way as the neutral axis later on. But essentially we are saying that if you have some kind of a center of this cross section, you're lumping all of that material there. Yes, for an analysis point of view, it is very convenient, and that's what we will do. But in reality, how it is that you want to keep the material as far away from this as possible, so that you have large moments of inertia, which means that the same amount of material, either you put it very close to the center or very far away from the center, you always will see that it is much better if you put it far away from the center, in the sense of it can take much more bending moments, it can take much more torque, it can take much more of many other kinds of loads. We will come to that shortly. But that is as far as the putting the material outside is concerned. What happens when you put the material outside? Automatically it starts taking the shape of a shell, because you are trying to spread a rod, whatever cross-sectional area it has, a thinner but hollow structure. You are pushing it out. Essentially it becomes like a thin tube, and a thin tube essentially is a shell-like structure. So that's what is the fuselage as well. You are trying to move the material out. So that helps in better resisting the loads which are applied to the vehicle. Similarly, if you are looking at from a point of view of the aerodynamic shape, you want the airfoil cross section for the wing. So if you want the airfoil cross section of the wing, you have to have the material outward. You can't say let me push all the material inside. You end up with a cylinder, and you know the flow through a cylinder, the drags are much larger compared to the lift that you can get out of a cylinder, and hence it's a very poor lifting structure. So if you want a lifting structure, you need to have an airfoil like configuration, whatever the specific airfoil you're looking at. But essentially all airfoils will try to push the material farther away, leading edge to trailing edge, and from the top surface to the bottom surface of the airfoil. Now that is again going to lead to a shell. Now coming again as far as the protection for the payload or the fuel that you are carrying, or cargo that you are carrying, whatever it is, you want more room. You know how constricted it is in the economy class toilets, for example. You want larger space. So you need to pay more for a business class ticket or a first class ticket in order to get such luxury, right? So essentially what we are trying to do is for better flight quality, or for the enjoyment of whoever is occupying the space within, you want greater space, and which again means that you are pushing the material out to create more space within. So again you are talking about shell-like structures, and then when you are pushing it in the other direction, essentially it becomes a beam. So you are pushing it in the cross-sectional direction, it starts becoming thinner and thinner and going more outer and outer, and essentially it becomes a shell-like structure. Now you are trying to elongate it as well, then it becomes essentially a beam. But there are certain structures that are more like a beam, certain structures more like a shell. We, in fact, towards the end of last class, we talked about some cases where it can be both, and how it is advantageous modeling it as in one way as opposed to the other. So now we are actually in a very lucky position, because all three are asking us to push the material out, push the material out, push the material out. Usually in design what happens is that there are conflicting demands. One asks to push the material out, the other asks pull the material inside. So then you have to kind of optimize and try to see where you can actually do. But these three primary functions, load bearing functions, as well as the functionality of having to take things along with you. It's not just the aircraft structure which needs to fly, but whatever is within, which includes the fuel, includes the payload, includes the control systems, and so many other things which are inside the aircraft. You need to carry all of them. You need more space to do that. It's not just one thing about weight, the other thing is about the volume that it occupies as well, and that's where we see that shell-like structures start coming in. So in that sense, it's a lucky combination, because all these three roles that we have talked about, discussed just now, whether it's the aerodynamic shape or transmitting the loads or containing something within, for all of them, as I just described to you in words, most efficient location for the material, which is the structural material, offering certain stiffness, offering certain strength, etc. in various directions. The most efficient location happens to be the outer surface of the vehicle rather than the inner location. So we try to move it to the outside. So vehicle outer surface, which implies that most of the transportation vehicles, be it on air, space, land or waters, you are ending up with vehicular structures which are shells. So that is quite clear from what are the requirements, and therefore based on the requirements we are saying that these have to be typically shell-like structures. Now there are two types. Initially, if you look at historically how it started with the Wright brothers flying 1903 December, Kitty Hawk, you are looking at much smaller aircraft taking just 1 or 2 people at the most and flying at fairly low speeds. When you are having less payload and when you are flying very slow compared to what today's aircraft flies, then obviously the stresses and strains are going to be very less. In other words, the material requirements are going to be less as well, in which case this alone is sufficient. This argument that we have made to say that we need shells and we will live with shells. And if you look at the way the construction was for the Wright brothers, you typically have fabrics which are going to be either in a monoplane or a biplane kind of configuration. Not only the Wright brothers, but also in the few decades after that, let's say 1 or 2 decades after that, most of them were of that specific kind. So essentially you are looking at fulfilling this functionality for smaller and slower aircraft. But what happens when we either make the smaller aircraft bigger or the slower aircraft faster, or both, in which case you have a faster aircraft which is fairly large, like let's say the Airbus aircrafts or the Boeing aircrafts. So many of them are so massive, at the same time they are flying at a fairly larger speed compared to some of our initial aircraft. In that case, still yes, we need shells, but what would happen is as the speed increases, you need more stress handling capability, which means the thickness required of the shell will be more. Similarly, if the aircraft wants to fly faster, the air loads will be more because of the faster speed. You know that the lift is given by half rho v squared SCL, which means it's proportional to the square of the velocity or magnitude of the velocity, and similarly the drag as well. So the larger the speed, huge increase in the lift and the drag, which means that a huge increase in the stresses, which means that I need a much thicker shell. So it goes to such a level at very high speeds and very large aircraft that you can't even any longer think of it as a shell. It becomes a fairly solid structure. So then we can have an ingenious way of looking at it, how those shells can be, instead of just a monocoque shell, or what we call as in the French monocoque, essentially means mono means single and C-O-Q-U-E, coque essentially means an egg. So essentially you are looking at an egg-like shape where you only have the shell. That is fine for slow aircraft, for small aircraft. But either one of them changes to the other extreme, then you will need so-called stiffened shells. Then we get into what is known as a semi-monocoque construction, which is what most aircraft today are, and that is why we deal mostly with shells and beams, and The rest of this course will predominantly be an ability to understand, analyze such shell and beam-like structures. Today we are just setting up the motivation for doing so. So what are these two types? The first one I talked to you about, okay, for low speed small aircraft, those are the so-called monocoque structures. So mono is the prefix and QUE essentially is the French for saying egg-like structure. And that's why if you look at an egg of any bird for that matter, it's fairly strong. You might be able to, of course, through an impact easily break it, but if you try to apply uniform pressure and crush it, it's very, very difficult to break an egg. It's especially the particular shape of the egg. Even though the material of the egg is not all that strong in terms of its, let's say, ultimate tensile strength or whatever, you would see that still the ability to withstand the load is much more, primarily because of the geometry. It's an ellipsoid kind of a geometry that you have, and that geometry is very, very special in terms of the ability to handle loads. So that is why this word itself comes from an egg-like structure, because typically these materials, if you have seen an eggshell, you will see that it's very porous. In other words, it's not even having a solid consistency, because it needs some breathing space for the yolk inside, which could eventually grow into an embryo potentially. But you would see that still, even though the material may not have large strength, the overall load carrying capability of a shell is fairly large, and that is what we are talking about over here. But once it becomes, as I said, larger aircraft or faster aircraft, then you would have to have, because larger vehicle, if you want more payload, you need to take a larger vehicle, means the cross section size is going to be large. In other words, if you take the fuselage and cut it anywhere, the cross sectional shape of the shell that you're going to have is such that it's going to encompass a very large area. So larger cross sectional size eventually means that you're talking about more loads, both distributed kind of loads and the so-called concentrated loads, which are also, as I repeatedly say, not really concentrated loads. Purely for idealization, we take it as concentrated loads, but distributed loads which are acting on very small areas, large loads acting on very small areas. So all of those loads are going to go up because your cross-sectional size has grown up, and also the loads that are acting on it are much larger now, either because of the larger speed and therefore lift and drag being proportional to V squared, and or also because of you're taking more payload and more fuel to fly larger distance, etc. So not only larger aircraft and faster aircraft, but also longer range aircraft means more fuel, and therefore again you're talking of a larger aircraft from a different reasoning purpose. Then what happens when these loads increase? Obviously the stresses, which is essentially a reaction of the structural material to what the environment puts upon it. The environment puts upon it certain loads, which is according to Newton's third law, an action, and now the material of the aircraft has to resist that, which is essentially a reaction. So every action has an equal and opposite reaction. So the reaction is what we are calling as stress. So have this distinction in mind. There is a load and there is a stress. Don't get confused between this. Load is coming on the structural material from the environment, whereas the stress is essentially a reaction of that structural material to that load which is acting, so that at any given place, if you take an area, there is an equilibration between the external load and the stresses that are offered on the surface. And similarly, if you take an internal material, between the adjacent materials on all sides of that particular material cell that we are interested in, there is an equilibration that is happening. So all of these essentially are from the principle of Newton's third law, where you have a symmetry principle in the sense of interacting force fields are going to be symmetric and opposite in some sense. Then coming to the fact that from that, because of the loads, all these stresses are large, and we already talked about different kinds of loads, the corresponding kinds of stresses also happen. Torsional loads causing primarily torsional stresses, compressive loads primarily causing compressive stresses, the bending loads causing primarily bending stresses. But again, depending upon the asymmetries in the geometry and or the material distribution, especially with composites, different kinds of layups, there can be couplings as well, that the torsional load is causing a compressive stress, or the bending load is causing a torsional stress, etc. All kinds of interactions can happen as well, but those are typically secondary compared to the primary result, and most of this course will be looking at that primary result and then looking at how to take that forward in terms of building blocks. So then once the load increases and therefore the stress increases, obviously to resist that much of stress we need more and more shell thickness to handle that. So that's how the shell thickness starts going up, and therefore the weight of the shell itself starts growing. So now what is the required weight for the shell becomes larger, but the very first reason why we wanted shell was that we wanted, as Patrick rightly pointed out, we wanted a more efficient, less weight, heavy structure, right? But now the fact that we want a better performance in terms of ranges or sizes and or speeds, then obviously the shell weight which is required starts growing up if we want to live with the shell alone. That's where the second guy comes in. On the top of this slide we asked why shells and beams. So far we have been addressing why shells. Now for higher performance aircraft, because of the shell weight going up, if we don't want that to happen, we still want to have an efficient flying vehicle, in other words less shell weight, then the only way is to stiffen that shell. That's what we are talking about over here. To support thinner shell, instead of having a very thick shell, you go for a thin shell even in those high performance aircraft, but instead of having the shell alone, which will anyway fail if you are trying to fly it that fast or with that much load, so then you have to have a stiffening kind of structure, which is something that we have learned from biology. The way our body or even the tree etc. takes the load is through a skeletal kind of a structure which is supporting the rest of the things that are attached to it. So that is essentially if you can think of our human skin as the skin of the aircraft, then it's not taking all the load, but it's the one which is exposed to the atmosphere, to the temperatures, to the pressure, etc. But it's not the one which is going to take the load. It's just going to receive the load and immediately transfer it to whatever is the next tissue which is attached to it. Eventually it's all going to end up with the skeleton which has to handle all of these stresses and strains. That's precisely what we are doing here as well. We introduce a skeletal structure, a set of stiffening members in both directions, typically an orthogonal network of them, almost like a fabric, how you're weaving things. You're weaving things in such a way that they're longitudinal stiffeners along the span of the wing. There are transverse stiffeners which are along the chord of the wing, and these two are attached to each other and in turn attached to the skin of the airfoil. Similarly, in the case of the fuselage as well, you have the skin of the fuselage, then you have stringers and stiffeners going along the length of the fuselage, and then you also have so-called bulkheads or pressure bulkheads and also various other frames that are there throughout the length of the fuselage, and each of these are interlocked with each other so that they can transfer the stress from one to the other. So you are supporting that thin shell, whether it's a fuselage, whether it's in the horizontal stabilizer, vertical stabilizer, or the wing, or any other flying vehicle or any transport vehicle for that matter. You would see that there are thin shells. Even in an automobile, if you take a car for example, you have thin sheet metals, but every here and there you have these large cross section rods going around, which are essentially creating the chassis of the vehicle, and that is essentially the load bearing structure that is there, which is going to take the load from the skin, the sheet metal, and then transfer it to whatever they are attached to eventually. So what do those stiffening members from a structural engineer's point of view mean? They are essentially beam-like structures and frame-like structures. The frames can also be thought of as made out of beams which are joined to each other either through welding or through some other means, but essentially we can put in the joint conditions for that, or we can think of it as an integral single beam which is having a certain initial curvature, or it's a piecewise beam in the sense that even if you have a structure like this, you can think of this beam and this column which are attached to each other, both are 1D structures, but together they can be treated as a single 1D structure as well. But essentially what we are looking at as frames or frames also eventually turns out to be made out of beams which are essentially one-dimensional structures as opposed to the two-dimensional structures that we already introduced. So that's the reason why we have these 2D structures and 1D structures on most flying vehicles, and of course on the other transportation vehicles as well, but more so because our requirements are much more stringent in aerospace. Now we call that, because we still have a shell, therefore we continue to call it monocoque, but it's not the shell alone but a supporting skeletal structure. So we introduce this word semi as a prefix to say that it's not fully monocoque, it's having a certain supporting structure underneath, a skeletal kind of a structure. Now what is the end result of all of this? In spite of the fact that I'm having a faster aircraft, a larger aircraft, a longer flying aircraft, a larger range, or even larger endurance for, let's say, reconnaissance or whatever, essentially higher performance, you're still having a lower weight because you're having a combination of shells and beams. Not only shells and beams, and that's why you're going to have a much lesser structural weight, and which means that also that the concentrated loads, so-called concentrated loads, are going to diffuse much more smoothly into the skin. Otherwise what will happen is these loads are, let's say, where the engine is attached to the wing, if say the engine is attached somewhere here on the wing, you see that one is the weight of the engine, the other is the thrust of the engine. These two are almost like concentrated forces, and if you had only the skin of the wing over here, it will very easily fail. But now at that location you will typically have transverse stiffeners called ribs, and also fairly large thickness spars going around, also stringers, etc. All of that will redistribute that load, which is first again encountered by the skin but immediately transferred to those attached stiffening members, and therefore the skin is safe. So that's how a lot of these concentrated loads will diffuse. Again, from the landing gear, for example, typically let's say the nose landing gear of the fuselage, or in the tricycle kind of landing gear, you have those parts which are attached to the rear parts which are attached to the wing. All of them are typically almost like concentrated loads. But if there were no stiffening structures close to where they are attached to the wing or the fuselage, then you would have a massive failure, and therefore that can be avoided by having these stiffening structures, which help not only to reduce the structural weight but also a smoother diffusion, a safer diffusion of these so-called concentrated loads into the skin. Okay, now that we have understood the reason to have shells, the reason to have beams, and the reason to have a network of them, a combination of them, what we call together a semi-monocoque construction, we will look at the parts of it and try to understand each part, its role, and then we'll see how eventually we will have to deal with each one of those parts with the typical kind of loads that it experiences. Okay, so this is more in terms of the nomenclature. You have similar kinds of structures in other transportation vehicles, be it on land, water, or tracks, even in space, but essentially within aerospace industry we have certain names given to each of these structures. One is of course the skin that we already talked about, the cover skin that you see over here. If you take any of the lifting surfaces, this could be a part of a wing, it could be a part of a horizontal tail or a vertical tail, but essentially you're having this kind of a structure where you see the skin on the outer surface that is your cover skin, if all of these inner things were not there, this would have been much thicker to resist the load. Now that it is fairly thin, we will try to see what all it can do. But before that, well, let's look at some of the other major components. You have the so-called spars, which are essentially like beams. So this is called as a spar cap. This is another spar cap, the upper spar cap and the lower spar cap. The upper spar cap is attached to the upper skin. The lower spar cap is attached to the lower skin, and in between they are joined by what is known as a spar web, right? Now this is almost like an I section. So you have a large flange on the top, a large flange on the bottom, and essentially a thin sheet which is in between them. Many a times this could be a sandwich kind of a construction with honeycomb, or it could be with foam if you're typically using composites as the plates for that. Now, if you other than this, which can of course have for larger aircraft, you may not have a single spar, you might have one more spar over here, etc. So there can be sometimes 3 or 4 spars too, depending upon the size of the aircraft that is involved. Now, in addition to that, there are also stiffeners which are running through the span of the wing, and those are what you see over here, which are essentially longitudinal stringers. Okay, so these longitudinal stringers could be hat shape. In other words, you have a shape like this, or it could have a channel or a Z cross section, and various other cross sections that are there, which we will see as we go forward when we work out actual numerical examples, etc. So then you're looking at those longitudinal stringers. Then we also have at certain locations along the length, especially where, let's say, you're attaching an engine or something, but even otherwise, you would have certain things which are having the almost the shape of the airfoil cross section, which are essentially covering this whole surface, and that is, but it might have certain holes in between to make cables pass through or fuel to pass through, etc. But it will essentially be a transverse stiffener as opposed to these which are longitudinal stiffener. So the longitudinal ones are along the span, which is for a wing. In the case of a fuselage, it will be along the length of the fuselage, and similarly the transverse stiffeners are along the cross section of that. In the case of the wing or tail, it will be the airfoil cross section. In the case of the fuselage, it will be either the circular or oval or elliptical shape of the cross section at different locations you have. And some of these will be much more bigger than the others, massive, capable of handling more loads. For example, in the fuselage, at the front and the bottom, front and the rear, we will have what are known as pressure bulkheads. So these pressure bulkheads will be complete, full, covering the entire cross section of the fuselage at those points, and will be able to handle the internal pressurization of the fuselage cabin in order to make sure that the aircraft doesn't give way. So all of these are individual components. We'll try to look at each one of them individually. So this is an example of a wing or any lifting structure for that matter, could be any of the tails, and this is a fuselage component. You see it has a very similar structure. It has the cover skin once again. If the cover skin alone was there, we would have called it monocoque. Now we are calling it semi-monocoque. It's a higher performance, and we are having all these stringers. So these are the transverse stiffeners that I talked about, these rings that you see, but towards the end they might become entire discs. So that is where you have a pressure vessel which is covered from the front as well as the rear, and those are called as the pressure bulkheads. Now these transverse frames are sometimes depending upon their sizes, and also the nomenclature varies from industry to industry. Sometimes instead of frames you call them rings for the obvious reason that they look like rings, and as I said, when they become more massive you are calling them bulkheads, right? Then we are coming to, we'll deal with each one of them separately. So the equivalent of those transverse frames, rings or bulkheads in the case of the wing or the tail is what we call as the ribs. Very similar to the ribs that we human beings have in the skeletal structure. Okay, so now let's look at the functionalities of each one of these. So let's start with the cover skin. The cover skin, though I'm showing for the cover skin of the airfoil over here for the wing or a tail, the same thing applies to the fuselage skin as well. So all skins typically transmit the aerodynamic pressure coming from the air which is flowing around the aircraft to whatever it is attached to, which is typically all these stiffening structures that you see. For example, at the bottom you see all these channel or hat-like structures which could probably be riveted, which was a very common practice in earlier day aircraft, especially metallic. It could be welded, or it could be bolted, or it could be adhesively bonded, or as it is in the case of a lot of today's composites aircraft, especially medium sized ones or smaller sized ones, where you would have these integrally manufactured in an autoclave along with the rest of the skin. So it would be a single part in other words. So that's the first function, to transmit the aerodynamic pressure to the stiffeners. The next thing it does is, because it's thin and it is forming a closed contour along with these spar webs. So for example, if you look at this is essentially a closed cross section, a part of a closed cross section. Similarly, this is another part of a closed cross section. It forms another cell. You have a third cell which is coming over here. So now this is a 3-celled structure. Each one of those 3 cells are part of a closed cross section, and that is going to have a much better ability to resist torques, as I was talking to you about. Even in a circular tube, if you have a thin slit, even if you're not removing the material, I told you, it loses its large part of its ability to handle torques. It will be able to handle only very less torque before it fails. So whereas here you're having a continuous structure which is hollow, and therefore these are very good at taking torque, and that's why the second functionality of the skin is to resist the torque and the shear forces along with the shear webs. So these of course are the shear webs that we are talking about, because the skin alone, if you're looking at it, is forming a large closed cross section over here, but along with the spar webs, which are also speaking about in terms of the material distribution, very similar to this. It's just that these are initially curved structures, whereas these are fairly flat structures. But even if you look at the airfoil cross section itself, at the bottom typically it's almost flat. So this is more like a plate or a panel as we call it. These are more like shells, but even there, if you have smaller portions, we typically call them as wing panels or tail panels. Now or empennage panels. Then the third function that you have is that it enhances the axial and bending stiffness which is provided by the longerons. Now I said that the spar cap along with these stringers are essentially going to offer a lot of capability of tension and or compression. So when the aircraft is flying, it is essentially having a lift, and the lift is trying to bend the wing upwards. The top skin is under compression. If the skin alone was, it could buckle and it could have other kinds of material failure as well. But now you don't have only the skin, you have these stringers, you have the spar caps on the top. All of them are going to take that compressive load on the top. Similarly, because it's bending upwards, the bottom surface is going to be under tension, and that tension is going to be shared not only by the skin but also all of these things. That is these two lower spar caps and all of these stringers which are attached to the lower skin of the airfoil. So even though the primary function of these stringers and the spar caps is to take those axial loads, either compression or tension, and therefore together they are offering resistance to bending, but the skin also has a non-zero area, and it also offers certain compression before it buckles, and similarly here it offers certain tension, and similarly when it's on the ground, because of self weight of the wing, these loads reverse, and the top will be able to offer tension, the bottom will be able to offer compression resistance. So that's as far as the cover skin is concerned. Let's take up the longitudinal stringers next. Sometimes in some parts of the industry they are called also as longerons, but sometimes a distinction is made between the stringer and the longeron, that stringers are shorter They may not run from end to end, from the root to the tip of a wing or root to the tip of a tail, but and similarly in the case of the fuselage, they may not run all the way through from the nose of the aircraft to the tail of the aircraft, but the longerons are much longer. They run almost through the entire length of the fuselage or the entire length of the wing or the tail. So those are the longitudinal stringers or longerons. And just like we looked at the various functionalities of the skin, let's look at the various functionalities of the stringers or longerons. The main functionality, as I just described to you, is to resist the axial load, either tension or compression, and because they are able to handle both in pairs, a set of the top stringers and the set of the bottom stringers together are able to handle, if one handles tension, the other handles compression, and vice versa, and therefore they can not only handle axial loads but also bending loads. Now in the case of a few fixed wing aircraft, this may not seem very important, but in the case of a helicopter rotor blade, because the rotors are rotating at a fairly large RPM, the rotor blades, the flex beams within them have very large centrifugal loads coming from the axial force, and therefore they need to be able to resist that axial loads as well, apart from bending due to the lift distribution. The second functionality of the stringer or the longeron is to increase the buckling strength of the skin. As I said, when the aircraft is flying, the top surface is having compression, therefore a tendency to buckle. So even before the material could fail, there could be a geometric failure in the sense that the skin tends to buckle. But as I already told in a previous class, the current designs to make the aircraft much more efficient, lighter weight and higher performing, you typically will allow the skin to buckle and operate in the post-buckling regime, and when it does that, all of the compressive load which the skin was taking earlier, which we talked about over on the top over there, we talked about over here, we are going to see that redistributes amongst the stringers and the spars, so that already the stringers and spars on the top were taking compressive load. Now because the cover skin on the top is buckled, operating in the post buckling regime, the compressive load that the skin was taking is also now equally redistributed in some sense between all of these stringers and the spar caps on the top. So therefore they are designed so that not only when the skin is taking the load, but even when the skin is not taking the load, they should be able to handle all of the load if at all it comes to such a situation. So that is what they do. They increase the buckling strength of the skin. Later on we will see that that simple example of a simply supported kind of a column that you have, you would have the Euler buckling load will be given by pi squared EI by L squared. In other words, it's proportional to the bending stiffness and inversely proportional to the length of the column. So the shorter the column, you are going to have a much larger load before it buckles. So what these are doing essentially is that they are reducing the size of the panel by having these stringers and also these, especially the transverse stiffeners. What they are going to do is to reduce the length of the cover skin, which is between two joints, and therefore you are going to delay the occurrence of buckling, and so that is one thing. But of course that is a functionality of the transverse frame, and we will look at it when we get there. The next thing that the stringers or longerons do, I'm of course explaining everything from the wing perspective, but the same thing holds over here. It's just that the overall cross section is of a airfoil over here. It is either circular, oval or elliptic over here, but nonetheless there's a 1:1 correspondence in terms of what all each one of these functionalities are. And so whatever I am talking about in listing over here is valid not only for the lifting surfaces but for the fuselage as well. The last thing that we are listing for the stringer is that it is able to arrest the crack growth in the skin by taking excessive axial tension. So in other words, the bottom, for example, when its aircraft is flying, is under a very large tension. Now that tension that is there now it is not taken only by the skin but by the stringer as well. So if at all there is going to be a crack or something, it is going to, let's say in the case of the stringer, this particular stringer, that because it's under very large tension, it has a crack along this direction along the cord, then it's no longer able to take that tension at least for a part of the length, which means that the skin has to handle that. So now of course it's not, the entire thing is not going to go to the skin, because very soon you're going to have another, either a spar cap or a stringer which is going to come adjacent. So at least for that amount of low transmission length, it should be able to handle. So that is essentially what we are talking about here, that the string, or the other way around, if the skin were to crack, then you would see that this tension will no longer be taken by the skin, and therefore that tension which was shared between the stringers and the skin is now taken only by the stringers, and it is designed such a way that it can handle that as well. So just like for compression, we said that after buckling the stringers should be able to handle even the skin's load. At the bottom, even after material failure and a crack developing, it can handle. And also if the crack is initiated and has started growing along this, if there were no stringer, it would have grown very rapidly along the skin. But now that it encounters a stringer, it acts like a bridge. So it acts, it stops, it essentially is like a security, that it stops that crack from growing as fast as it would have otherwise. So that is what it's saying here, arrest the crack growth in the skin by taking the excessive axial tensions. That's as far as the stringers or longerons are concerned. Next we'll look at this spars. Very, very important structural member, one of the massive ones, typically along the entire length of the wing or the tail, and these are made out of two parts. We saw here the spar caps on the top, the spar caps on the bottom, and then of course the shear web. Let's start with the spar caps. Now the spar caps functionality is very similar to that of the longerons. It's just that these are concentrated areas that are there which are able to take either the tensile or compressive loads, both put together with what we call as normal loads. But these are usually much larger in cross section compared to the stringers, and therefore they can take even more than a single stringer. But of course there are many more stringers compared to the spars, so therefore they can as a team do much better as well. But essentially it's not this or that, but this and that, and therefore all of them together are going to resist your normal loads, both tension and compression, tension on the bottom and compression on the top. So I think that's kind of yeah. So the caps of course are same as longerons, but as I said, because they are larger in cross sectional area compared to the stringers, they have an amplified functionality, which is what I just described in different words. The web on the other hand is not going to be good at taking axial loads. It's just like the skin of the cover skin. It is essentially good at taking shear. So all these thin panels, unlike the beam-like structures which are the stringers and spars, are going to be better at taking shear loads. In fact, that is the reason why it is even called as the shear web. So that whatever you have over here in between is essentially called the shear web or the spar web, and that is and most of the shear is coming from the torque, as I described, the pitching moment, and also the fact that you have a non-zero moment arm, because many of these so-called concentrated loads are away from the so-called center, which could be the neutral axis or whatever you or shear center, or what we call as the center of twist. All of these are different concepts which we will introduce later, but essentially some kind of a centering around the cross section, and you would see that there is torque, and the torque will essentially be resisted as shear, and in resisting the shear, these spar caps are no good, the stringers are no good. They are so good in axial loads, normal and both compressive and tension, but they are not so good in shear. For all of that you need the cover skin and you need these spar webs, which are typically like honeycomb structures or whatever. So you essentially resist the torque and also the shear forces. Now for example, the lift distribution that you're going to have is not only going to cause bending, but is also going to cause transverse shear. So there's at any given cross section, if you cut, we will see that there is a resultant bending moment and there is a resultant shear force. Now that bending moment is going to cause compression and tension on the top and the bottom surface, but the shear force is going to cause shear stresses on the cross section, and they're going to be much larger in between rather than on the top and the bottom. These are of course much smaller compared to the axial loads or axial stresses, but nonetheless something important that you have to deal with. When you're trying to do that, you have this in between the spar webs, which will take the shear distribution coming from the lift distribution. Similarly, the skin here, if you see, there's a drag and the thrust. So the difference between them is going to cause a shear force in this direction, and that shear is going to be predominantly be taken by the top skin and the bottom skin. So that so in this case we are now talking only about the stringers and longerons. Sorry, we were talking about the web of the spar. So we are saying that it resists the torque and the shear forces along the skin. Then the next thing, is the transverse frames or ribs. Including the rings and the bulkheads that we talked about in the fuselage, as well as the airfoil shaped transverse ribs in the lifting surfaces. One thing is they maintain the cross-sectional shape. If they were not there, you can see that these are fairly thin and flimsy. In spite of all these attached to it, they can easily change the shape, and if they change the shape, the airfoil configuration that the aerodynamicist asked for is no longer going to remain, and therefore the lifting performance is not going to be as good. The lift by drag is not going to be as good as it was designed for, and therefore everything is going to go for a toss in terms of the overall aircraft design. So therefore it's very important to maintain the cross-sectional shape. Similarly in the fuselage also, you don't want the fuselage to start swelling in one direction or shortening in some other direction. It's going to cause a lot of trouble in terms of the contents of the fuselage. So in either case, these rings, as you can very clearly see, is going to maintain a certain circular shape or oval shape or ellipsoidal shape, elliptical shape over here, and similarly it's going to maintain that airfoil cross-sectional shape over there too. So that's one of the primary functions of the transverse frame or rib. In the case of this, it's called frame or ring or bulkhead. There it's called a rib in the case of lifting surfaces. Now the second functionality is typically in terms of distributing the concentrated loads. So as I said, you will typically have much larger rings or much larger transverse ribs where something else is attached to that. Maybe a landing gear is attached, or an engine is attached, or some other bay is attached. In the case of fighter aircraft, it could be the weapons bay where massive weapons, missiles are attached to it, and all of that are going to be very heavy, and when they are launched, it could create an instantaneous force which is very large, which could cause very large bending as well. But if you are attaching it to the area of a skin where there are no transverse stiffeners, the potential of failure of that is very, very large. So typically you will attach all of these heavy structures, be it the bay, the weapons bay, or ammunition, that is, or you would have typically the engines or the landing gear, etc. Those concentrated loads have to be distributed into the skin, and the transverse frames or ribs play a very important role over there. The next thing is in terms of redistributing stresses around structural discontinuities. So there can be structural discontinuity in the sense that you might stop suddenly a stringer, you might stop a spar because the spar may no longer be required close to the tip of the wing because the lifting loads are very low over there. So you might not need such a massive spar coming from here to there. So sometimes it is gradually reduced in size. Sometimes it is a stepwise reduction. Sometimes the spar can stop suddenly, and then no longer you have a particular spar. Instead of 3 spars, you have only 2 spars, or even 1 spar as you go towards the tip. So when you are having such structural discontinuity, where there is a change, a sudden change, a drastic change, there can be severe loads, and that's where if you can put a transverse rib in the case of a wing or a ring in the case of a fuselage, you would see that that can be kind of diffused, that structural discontinuity. Just like what we are talking about here is a loading discontinuity. Now we are talking about a structural discontinuity, a geometric discontinuity that is there. Both are handled by these transverse stiffening structures. The next thing that the frames or ribs do is to increase the buckling strength of the stringer or rib. I already mentioned this to you, that if there were no transverse ribs at all, the skin length will be so large, and even a small axial compressive load can cause it to buckle very soon. But now that you have these transverse ribs along the span of the wing, you're going to see that the effective length of the panel along the span is going to be reduced because it is joined at two ends by these ribs, and therefore it's not the entire span that is the length of the structure that we need to consider for buckling, but the panel between two transverse stiffeners, and therefore that panel length is much shorter. And I was talking to you about a 1 by L squared, an inverse square relationship, and therefore the closer these transverse ribs are, the lesser the possibility of that buckling happening, which is what we are talking about here, to help the increase the buckling strength of the stringer. And the second next thing is to help the skin take hoop stresses as well. Especially in this case, you're going to have internal pressurization. Even compared to the longitudinal loads, for a near circular cross section, you're going to have almost double the hoop stress, which means that you're going to be able to handle that, and to large extent the frames helps the skin to handle, because it is going to make sure that the skin doesn't blow up entirely at different periodic intervals when they are spaced out, right? So appropriately spaced out. So it helps the skin to take the hoop stress as well. So with that, we'll come to the end of today's class. So this is going to be your assignment, which you will be presenting at the beginning of the next class. The rules remain, of course, the same. I'll go over summarizing the rules also on the next slide before we wind up today's class. What is the assignment? Assignment is essentially based on what we learned today in terms of the various constructions that we typically have for aircraft structures. In particular, we are going to look at examples of the various kinds of structures, like what I talked about. If you have just skeletal structure alone, that is those ribs, stringers, and the spars, etc., without the skin. So that's essentially your truss, or in other words, you might have the skin, but the skin is as good as, let's say, a fabric or something, which is hardly going to take any stress, or which is what was very common in the first 2 decades of the history of human flight. After the brothers, you typically had mainly truss-like structures. So I want 5 examples of truss-like structures. Similarly, 5 examples. Maybe let's make it 4 examples, so that each of you, we have 4 in the class, including Nilesh, and then we could have 4 each. So change this to, instead of 5, make it 4. So find 4 examples. For each of you are required to find one of these. One truss example, one monocoque example, and one semi-monocoque example, so that when we put together for the whole class, it will become 4 examples of each, right? So now I want you to name, of course, the aircraft, bring some pictures which you can project to showcase indeed that is a truss-like structure. Something is a monocoque structure, which means that it must be typically a smaller and slow-speed aircraft flying for a small range, typically an older aircraft. But there are some newer construction also, especially the aero modeling kind of the ecosystem typically works on these because they are dealing with smaller speeds and smaller sizes. So monocoque constructions and semi-monocoque constructions. Now this is like an encyclopedia of all the aircraft that have ever been produced by humanity, including those which are yet to be produced, which are still in the design stage. The Janes is a group which kind of brings together all of that. They not only have these for aircraft, but for various other kinds of structures as well, like missiles and or ships, etc. But for aircraft, they have a specific set of volumes which they keep updating every year. So Jane's All the World's Aircraft will be one good source. Flight International, a magazine, would also be a very good source for looking at it. It also has a good website, so you can look at Flight International. And of course, as always, trying to utilize the large language models, the chat GPT and using GPT-4 and or the Google versions of it, Bard, etc. You can try to get some information based on that. Then what is the exercise? Once you get that, wherever possible, it's very difficult to get this data, but wherever you can, try to get the skin thicknesses. So because that's what we were talking about today, that monocoque, it was good because you ended up with a shell, but as the vehicle's performance requirements were more and more, it became thicker and thicker shell, which is why we wanted to stiffen it. So the skin thickness plays a very, very critical role. So we want to see for your monocoque example, what is the skin thickness, what is the skin thickness for the semi-monocoque, and for the truss also, to get the airfoil shape, you will typically have fabrics which are not at all stressed. Okay, so those also will be having a certain thickness. So wherever you can get your hands on to get that information on the skin thickness, we want to plot it as a size of the aircraft. And one way of measuring the size of an aircraft is either by measuring the length of the fuselage or the span of the wing. So tip to tip, what is the distance? That is essentially your wingspan. So the larger the wingspan, the larger the aircraft typically. Though it's not necessarily true, because you could have very large aspect ratio aircraft, or you can have very short aspect ratio aircraft, etc. But to not complicate things too much and not involve too much of aerodynamics, etc. over here, we will just plot it versus wingspan. So once you plot this, obviously these are going to be points for each one of these, and I don't not for individual, but all of them, all the things that all four of you collect, we put together on the same plot. So on that same plot, you put for the truss-like, the monocoque and semi-monocoque, use different symbols to indicate them. Maybe some would be circles, rectangles or triangles, etc. So you indicate each one of them, and then you also similarly plot another way of measuring the size of an aircraft, the overall weight, the gross takeoff weight. What is the maximum takeoff weight of the aircraft? Okay, not the empty weight, but the maximum takeoff weight of the aircraft. So the gross weight, again, you that on the x-axis, you plot on the y-axis, the vertical axis, you plot the skin thickness again. So again, in both of these kinds of plots, I want you to comment. So this is the most important part of the homework, is the fourth point over here, where you need to comment if you observe certain clusters are taking place somewhere. So all these points are not kind of spread out randomly, but you will see some clusters happening at certain locations. Can you comment on that? Why such a cluster is happening, which will showcase the kinds of aircraft that you're dealing with, which are the truss-like, monocoque and semi-monocoque constructions. These will typically be at certain clusters. So I want you to put the cluster of points on each of these two plots. And then whatever source from which you're getting all of this information, I want you to upload into our Microsoft Teams, so that we can kind of cross-verify with the data that you have. So as I said, the skin thickness data is very, very difficult to obtain. So you have to search, research, beg, borrow, but of course don't steal. In other words, proprietary data and things like that, if at all some of us can lay our hands on. That's not what I'm looking for. We are looking for what is available in the public domain, including through LLMs, of course. But we want to put together all of that data and see if some of the things that we talked about in today's class, how relevant are they from a numerical sense, from a practical sense, from an actual aircraft sense. So with that, I will also leave with certain thoughts in terms of summarizing certain things that I have already told you about our homeworks. Going forward, we'll have a lot of numerical homeworks. So far, this third homework also is not so much of a numerical homework, but soon we will get into actual structural analysis for which we have built up the motivation so far. Now, once you get into that, and even today's assignment that I am giving, which you need to present at Thursday's class, I would want these rules to be kind of followed. So it's just a reminder because already we have gone through these game rules. So first of all, these are all team games. In other words, we're not going to be scoring individually for each of you. It's as a team that I'll be giving the marks. So therefore, the internal team games are also a part of the learning process. In other words, there's a lot of things that which you will do here which will not be actually directly covered in the class, and therefore you will kind of benefit by doing this learning supplementary to what I am teaching over here. So it's part of what our learning process. And as I've already told you, even in the email that I sent to you before you left the US, this is a place where you're not going to be competing with anybody else but your own past self, so that you can become better and more knowledgeable and more useful in terms of being a structural analyst. So you're competing with your own past self, which means that there are certain strategy tips that I would like to give you, which you would like to follow right from this assignment for all the other 15 odd assignments that you'll have through the rest of this course. So I want you to utilize all the relevant resources that you can lay your hands on, and because you're a team, don't duplicate each other's efforts. Try to meet and divide the tasks between yourselves, so that as a team you can bring in much more to the presentation in the next class. So that means LLMs, of course, apps that you have, many different apps. There are books, internet, forums where you have mechanics discussions, structural analysis discussions, etc. Friends and even enemies, if you have any, cite them. It's very important that you cite all of these references. It's a good professional practice that we cite them, even if I don't want it all cited at the end where we don't know what connects to what, unless we are having some kind of a numbering system to go back and forth. But because this is a presentation, I want the citation to be done at the time when you're presenting an information. This is where I got it from. This had certain limitations, and therefore this is how I overcame them. So you cite them, written preferably, but if it's too long, then even orally you can mention, especially about the LLMs, etc. But in a contextual sense at the place where they are invoked. Then I want you to talk about how useful those resources were in terms of their specific input and utility. And then most importantly, what was the limitation? Especially with the LLMs, you will see sometimes the answers are of no use or gibberish or hallucinations. So then how do you rephrase the prompts and the questions in order to come up with better responses, and how you utilize them? So how you overcame those limitations, that's very important thing going forward, not only for this course but for even your other courses and the career as well. Now, what I found in almost my quarter century of teaching is that one of the best ways to learn is to teach, and especially when you're teaching smart kids like you from Georgia Tech or IISc, we see that the kind of perspectives that we get when interacting with students is very, very interesting. And part of that teaching is also mentoring yourselves. It's a peer mentoring you have as part of a team, that you try to help out each other in what they are getting stuck up with, or trying to help them move forward, because you want to move forward as a team. So that's essentially what we are looking at. So which means that if this time, of course, we are talking about the different kinds of categories, trusses, semi-monocoque and monocoque construction. Each of you is going to choose one from each, so there's no difference between what each one of you is going to do, and eventually you are going to pool it all into two plots and get the information from that. But going forward in the numerical examples, that numerical homeworks that we will have in the future classes, we will see that there are certain problems in which only Patrick might work, certain in which only Nilesh or Alexandra might work, and some in which only Aryak will work. When you are trying to allocate between that from a problem set, I will not tell you do this, you do that, or you do that. It's part of your teamwork to see how you distribute it, and that's where the hare and tortoise story comes in, into one part of it, where we talked about core competencies. So you identify and you know, you've been around together with each other for almost a year or two. So you know the strengths and weaknesses of each other, which of course are not static. It's going to, your strengths are going to increase and your weaknesses are going to decrease, but nonetheless, what is the current state? Based on that, what one of you can do better than the other, based on that you try to divide the problems, so that, and of course sometimes you'll see tougher problems and simpler problems in the same problem set. One might be doing a simpler problem, one might be doing a tougher problem. Make a deal that in the next homework, the other one, other way around, the one who worked on the simpler problem will work on a more complex problem in the next homework, and so on, right? So as I said, there are no individual scores. I'm scoring for the team as a whole. That's why I want you to kind of help each other out. And then, as I've been repeatedly saying in earlier classes also, neither the class nor the homeworks are going to be goal oriented. What is more important for us to be process oriented. So when I give the homeworks, I will even give you the final answers for all of those, so that you can cross verify once you solve the problem whether your final answer is correct or not. So if there's some mismatch, then you can see if there is something that's gone wrong in your solution process, and you try to address that and come up with the right answer. But what is more important for me are the steps, the process through which you have arrived at that, okay, rather than the final answer, which anyway I'm going to give you as part of the homework itself, which means that you will use these slides which you present, and it need not always be slides that you present with. You could use the whiteboard as well, or just talk, or use combinations of these, whichever is more appropriate for a particular homework. You can use combinations of those, right? So use slides if at all you use. If you don't use, well and good, but if you do use slides, use them only as skeletal prompts, just points, major points, and you are filling in through what you're writing on the whiteboard, or you're explaining in words orally, so that oral description will take care of it. And when you're doing that, don't skip any steps. Go through step by step. Even if you think that is obvious or silly or trivial step, I want you to go through it. Think of me as a dumb head, and there's another person in the audience, maybe smarter than me, but think of us as dumb heads, but essentially try to teach us step by step what is going on, so that we understand we have gone through that process, is not jumping from one to the other abruptly. So don't skip the steps. Of course, your slides can skip the steps, but when you are explaining either on the whiteboard or orally, try to fill in for that, so that we understand where we go from. Be very careful about units. Sometimes there might be a mixed system of units, and so you have to, and you will see that in the skin thickness example also. So many of the aircrafts you might find the data in inches, some in millimeters, etc. Convert them all to a particular thing. I leave the choice to you, either inches or millimeters, and similarly the weight also, whether it is pound force or it's a kilogram or whatever, you try to put that. SI units are preferable, but I leave it to what you are used to. So that's another thing. And then be very, very precise when you're saying, let's say, put an integral. Make sure you put the integrand with respect to which you are integrating. If it's an definite integral, put the limits with respect to which you are integrating. If it's a vector that you're differentiating, put the frame with respect to which you're differentiating that vector, because all vector differentiations are frame dependent. So these are things that I want to keep you to keep in mind. So some of the things are not of course valid for today's homework, but they will be valid for many of the other homeworks. The other most important point, last but not the least, or in fact the most important, is that I want you to very clearly state the assumptions. Moving from one step to another, I said you don't skip steps, and when you go from one step to another step, especially the major steps, you have to list all the assumptions. Don't list all the assumptions at upfront in the beginning. Where you are invoking that assumption, and therefore you can move from one step to another step in the logic. I want you to state those assumptions and also the relevance of those assumptions. Is it really valid in a real life kind of a situation? How important it is and things like that. I want you to do it as many steps as possible. Thank you.